Hello, welcome to another video. It's been a little while since my last one, I think. But yeah, I've got a nice little thing here to solve, which is show that the square root of 3 is irrational, and the way I'm going to do it is proof by contradiction, which is the same way you would prove that the square root of 2 is irrational. It's a very well-known proof. It's kind of the go-to proof if you want to give an example of proof by contradiction. You say, oh, okay, well, I can show that the square root of 2 is irrational by proof by contradiction. I'm going to use proof by contradiction to show that the square root of 3 is irrational. Take one step up. So, first thing we're going to do is we are going to say, right, assume that the square root of 3 is rational. So we are going to say, we're going to assume that the square root of 3 can be expressed as in the form a over b, which is the general form of a rational number, and the conditions for this is that a and b are both integers, and the fraction above is in its simplest form. Okay, so what we're going to do, we're going to square both sides. We're going to get rid of the square root. So we can say that 3 is a squared over b squared. We're then going to bring the b squared up. We're going to multiply both sides by b squared, so we can say 3b squared equals a squared. I'm then going to subtract b squared from both sides, so I can say that 2b squared equals a squared minus b squared. Now I'm going to rewrite a squared minus b squared using difference of two squares. Well, difference of two squares. It's already in the difference of two squares, but I'm going to go backwards, and then I'm going to rewrite this as 2b squared equals a plus b, a minus b. So I have now got this equation here. If we look at the left-hand side, 2b squared, any number, it doesn't matter if this b squared is even or odd, once you multiply it by 2, it becomes even. So we know that this left-hand side is even, and since we have an equal sign in between these two expressions, the right-hand side is also even. So a minus b, a plus b result in an even number. Now, what are the ways in which to generate an even number if you multiply an even number by an even number by an odd number, or an odd number by an even number? So it seems that we have three conditions. We have three conditions in which we can generate 2b squared as an even number. We can say that a plus b is even, and a minus b is even. We can say that a plus b is even, and a minus b is odd. And we can say that a minus b is odd, and a plus b is even. So that's what it is on the surface. However, and I'm going to go to the next slide for this. So three conditions where a squared minus b squared is even. So I've just rewritten the a minus b, a plus b as a squared minus b squared. If we look at a minus b, and then we look at a plus b, if we want to go from one to the other, we're looking for the difference between these two, we have to add 2b to get from this here to this here. Now, if a minus b is odd, and we add an even number to an odd number, that gives us another odd number. So a plus b is also odd. And this won't do. This is not one of our conditions in which we said before, we said that there are three conditions, and we now know that neither number can be odd. Because if one number is odd, the other number must also be odd, and vice versa. So if we go backwards and we change the colour of our pen to purple, we can now say that, right, this can't be the case, and this also can't be the case because neither of the numbers can be odd. The only conditions that we can satisfy is where both numbers are even. So, therefore, both a minus b and a plus b must be even. Now, if we look at a minus b, if we look at a plus b on its own, and we look at a minus b on its own, if we want this to be even, what a and b must both be, sorry about that, a and b must both be both even or both odd. If we add an odd number, so let's say 2k plus 1, and we add an even number, 2k, we get 4k plus 1. This is an odd number. We are looking for the whole thing to be an even number. If we have two even numbers, obviously it gives you an even number, say 2 and 2 gives you 4, and then we add 3 and 3, that gives us 6. When both numbers are odd, or when both numbers are even, and we sum them together, we get an even number. So both a and b must be even or odd. And the same is the case with a minus b. If you take the number 7 minus 3, so an odd number subtract an odd number gives you an even number, and then 8 minus 4, the difference between two even numbers, gives you an even number. So it's the same in both cases. So we know that a and b must both be odd or must both be even. However, a and b can't both be even. So if a and b are both even, we can say that a equals 2k and b equals 2l. Now if we go back to our original equation, we said that the fraction above is in its simplest form. If we write our new fraction, if we write a over b as 2k over 2l, well, we can reduce that further to create k and l. And now we're just back at square one. So this is a contradiction of our original condition. So we can now say that a and b must both be odd. So now we're at the sole condition where a squared minus b squared is even, a and b are both odd. However, if we investigate this further, and I mean, you know that you can kind of tell that, you know, I'm kind of gearing us towards a and b can't both be odd either, because, you know, the whole point of this is it's a contradiction. Everything that I'm trying to prove is going to become wrong. So a and b are both, so, but for the time being, we assume that a and b are both odd. Let's take our a and b and let's call them odd numbers. So let's say that a equals 2k plus 1, and we're going to say that b equals 2l, to capital L plus 1. So if k is any number, 2k plus 1 makes it an odd number. If L is any number, then 2L plus 1 makes it an odd number. So that's where we're at. So I'm just getting my paper that I prepared. So let A equals 2k plus 1, let B equals 2L plus 1. Sorry if you can hear all that. If we go back to our equation here, or we just write it as a squared minus b squared, so 2b squared equals a squared minus b squared. And we substitute in our values of a and b, now that we know that they're both odd. 2b squared equals blam 2k plus 1 squared minus blam 2l plus 1 squared. And we expand. So we get 4k squared plus 4k plus 1 minus 4l squared minus 4l minus 1. and the 1's cancel, and what we're left with is 4 is the common factor of everything, k squared plus l squared plus k plus l. Oh, no, sorry, not... There we go. That's right. Yeah, so the l's are negative, sorry, and the k's are positive. However, and this is the clever bit, I think. If you can now see that 2 and 4 are both coefficients. We can reduce both sides. If we reduce this side by 2 and we reduce this side by 4, we get left with 2 on this side. b squared is 2 times something. So we don't know what the sign of k squared minus l squared plus k minus l is. However, if we multiply it by 2, it generates an even number. So we now know that b squared is even. If b squared is even, b is even. But hold on a second. A squared and b squared are both odd. But we've just shown that b is even. Therefore, we have contradicted ourselves, and we have now shown that the conditions for which the square root of 3 is an irrational number are impossible. So therefore, the square root of 3 cannot be expressed as a over b. And that is my fun little proof into showing that the square root of 3 is not a rational number, cannot be expressed in the form of a rational number. Thank you for watching. I thought this was quite a fun little video. If you enjoyed it, like it, comment, do the things, and I'll see you next time.